we started to discuss the error correction theory. Now our goal is to consider in detail the classical 3-bit code, in which every bit 0 value is replaced by a code word of 3 zeros and every bit with 1 value is replaced by a code word of 3 ones. The 3-bit code is a code with repetition. It means that this code is formed by the source information repeated many times. The 3-bit encoding scheme is depicted on the slide. Firstly, the pair of auxiliary bits in the state 0 are added to the source bit A. Then the A bit encoding via two CNOTs operations is performed. During the encoding, the A bit as a control bit and two auxiliary bits act as a target ones. As a result, the bit A is turned into the logical bit AL. Thus, one of these transformation chains could be performed. If the value of the A bit is 0, then as we add the auxiliary bit, it turns into a sequence of 3 zeros. It will remain in the same state since the CNOT operations will not change the auxiliary bits. If the value of the A bit is 1, then as well as we add two auxiliary bits in 0 states, we obtain the sequence 1, 0, 0. After that, the pair of CNOT operation turn this sequence into 1, 1, 1. To be definite, assume the logical 0, that is the code word of 3 zeros, to be the initial state of our logical bit. Since the error probability equals p, the absence of errors probability equals 1 minus p for each bit. So, the probability of no error in all 3 bits is the product of no error probabilities in every single bit and equals 1 minus 3 to the 3. One bit could change while other two will remain unchanged with the probability of p times 1 minus p to the second. One bit could change while the other two will remain unchanged with the probability of p times 1 minus p to the 2. Since the error may occur on each of the 3 bits, this result must be multiplied by 3. So the probability of error in one bit equals 3p times 1 minus p to the 2. This corresponds to the code word 001, 010 and 100. If we assume that 2 bits have changed, then the probability must be 3p to the 2 times 1 minus p. Finally, the probability of the error on each bit at once equals p to the 3. We depicted the change of the code words 000 and 111 on the slide. As we have learned before, not all of the errors are correctable. A code word encoded via the 3-bit code couldn't be properly decoded if 2 bits have changed. For example, a code word 000 can turn into a code word 101 as a result of 2 single bits errors. But at the same time, the code word 101 may occur as a result of one error in a code word 111, and thus we will not be able to find out whether the code word 000 or 101 was initial. Such circumstances depend on the quality of the information channel and restrict the 3-bit code's applicability. As can be seen from the example we discussed, if the single bit error has a probability of p, then the total probability of change in code words 2 or 3 bits must be less than p. It means that the probability of uncorrectable error to occur in the logical bit must be less than the single bit error probability in the not encoded bit. Only in this case, the 3-bit code is effective. So, if we sum up the probabilities of 2-bit and 3-bit errors that are uncorrectable, you can see them on the slide, we obtain the condition for p. Here we get 3p to the 2 times 1 minus p plus p to the 3 is less than p. It follows from this inequality that the 3-bit code is effective only if p is less than 1/2. Otherwise, the 3-bit code does not satisfy the redundancy principle and one has to use a greater number of auxiliary bits. Further, we consider only correctable errors which change the value of only one code words bit. The question to answer is how to restore the initial code word out of a distorted one. The simplest way to do this for codes with repetition is the bitwise search and the finding of the so-called majority value. The majority value for the 3-bit code is just the most frequent bit value. One has just to find out what is greater, the number of ones or the number of zeros. For example, it's obvious that if there was no more than one error, then the initial code word for the words 001 or 010 or 100 was the code word 000. However, this method of error correction is not effective in a general case. That's why the parity comparison for the code words bit pairs is being performed. This is done by the XOR operation or the addition modulo 2. The bits with 0 values are assumed to be even, and the bits with the values of 1 assumed to be odd. Thus, if 2 bits in the pair have the same parity, these are 0, 0 and 1, 1, then the XOR operation result will be 0. If the 2 bits have different parity, the result of XOR will be 1. In the case of 3-bit code, it is enough to compare parities of first and second bit and then the parities of the first and third bit. Let the initial code word be 000. Then we may obtain one of the following results. The first one. If the parity of the first code word's bit, which value was brought to the ancilla bits, matches the parity of other bits, then there was no error. So the code word remains 000. The second situation. If the parity of the first bit matches the parity of only one ancilla bit, then the error was in the ancilla bit. The corresponding code words are 010 and 001. So one of the ancilla bits had the value of 1, while the first bit and another ancilla bit had the value of 0. And the third possible situation is when the first bit's parity doesn't match the parity of ancilla bits at all. In this situation, we have an error in the first bit. The corresponding code word is 100. Thus, instead of making the bitwise search and the majority value finding, which requires at least 3 operations, one may compare the parities of first bit with the parities of the ancilla bits, and this will require only 2 logical operations. We emphasize that we do not measure the value of each bit, but we compare their parities. As we will see later, such an approach in the quantum case is essential. We also know that the parity checking provides one with sufficient information about errors occurring in the channel. The information is also called an error syndrome. Consider a certain commutation scheme which allows one to restore the initial code word totally using the information on parity. So, the error syndrome is being measured at the beginning. The scheme is depicted on the slide. The AENC code word is the source code word. The error syndrome is written in the 2 auxiliary bits which have 0 values at the beginning. As can be seen from the scheme, the error syndrome measurement is performed using 4 CNOT operations. The first 2 CNOT operations compare the parities of the first and the second bits, and the next 2 CNOTs compare the parities of the first and the third bits. Let's see how the bit error correction is done. So, we have 3 initial bits, 1, 2, and 3, and 2 ancilla bits, C1 and C2. So, suppose we have A1 equals A2 equals A3 equals 0. So the 3-hour bits equals 0. And now suppose the error changed the first bit. It means now that A1 is equal to 1, while A2 equals A3 equals 0. Okay, what we have got here? The first C0 element. Our A1 bit is equal to 1. And the first ancilla bit changes its value to 1. Since our second bit is equal to 0, the second C0 element doesn't change the ancilla bit, since the control bit equals 0. The third C0, again, since our control bit is equal 1, change the value of the C2. And the last C0 element, since our third bit equals 0, doesn't change a thing. So, the result here is the following. The values of ancilla bits are C1 equals 1 and C2 equals 1. Then these guys are used as the control bits in the Toffoli elements here. Since we got them equal to 1, this Toffoli gate will trigger and change the value of A1 from 1 to 0. And thus, we'll obtain the correct code words 0, 0, 0, which we had at the beginning, as a result of our error correction procedure. If we have information on the error syndrome, we are able to restore the initial code word A-enc via 3 successive Toffoli gates. The last 2 of them had the values of the control bits inverted, and it is depicted by a hollow circle. These Toffoli elements will actuate if the control bit, which is depicted by a black filled circle, has the value of 1, and the control bit, which is depicted by a hollow circle, has the value of 0. It's easy to show that the first Toffoli gate corrects an error in the first bit, the second one corrects an error in the second bit, and the third one corrects an error in the third bit. Of course, the error syndrome has to be used. We note that this scheme allows one to restore the whole code word at once. For the detection and correction of single bits errors, the simpler schemes could be suggested. However, in order to perform computations that consist of a large number of logical operations, it's more efficient to do the error correction procedures entirely for the code words. We've been assuming that the coding-decoding procedure goes without errors. However, it's not always so in practice. That's why it's much more convenient at the next computation step to use the code words obtained earlier instead of doing the extra encoding-decoding procedures. That's all about the classical error correction procedure. In our next lesson, we'll discuss the quantum case. Thank you for your attention.